Good afternoon, my YouTube viewers. It's Crystal here. I'm here this afternoon because I wanted to do an analysis of variance on the PlantGrowth CSV file in Python using Google Colab. And so I'm also going to do it in R. I'm going to do both Python and R for this analysis of variance. But we will start out with Python. First thing I'll say is the analysis of variance is where you compare the means of more than two arrays of data. But in this instance, we're only going to be using two arrays of data and not more than two because it's on the PlantGrowth dataset. The PlantGrowth dataset is part of the R dataset, but I was able to get it off of the GitHub account. So in Python, what we will be doing is we will be using the CSV file, but in R, we will be using the inbuilt file. So for Python, the first thing we're going to do is we're going to import the libraries, and that's a difference between Python and R, because Python is a general purpose language, and so a lot of the things that you want to do on it, you need to import libraries to do what you need to do. But R is a statistical programming language, so that means that a lot of the functions concerning statistics are already inbuilt into R. So that's a difference between Python and R. I mean, I will say that I personally prefer using Python because I can use it in Google Colab, and Google Colab now has Gemini, and Gemini actually helps you with your coding. So that's a good thing about Google Colab. Whereas R, it's hard to find a compiler for R that's free, and basically you can actually download the R compiler, but it's not on Microsoft Store, and I don't want to upload anything onto my computer that's not on Microsoft Store, because if it's on Microsoft Store, apparently you have a little bit of safety, whereas you don't have that safety net if you upload it from another source. And that's not to say that the R programming website isn't a good source, but they don't put R on the Microsoft Store website, which I believe they should. Even Python, I've got Python 3.13, I believe, on my computer because that was on the Microsoft Store website. So I can actually use Python 3.13 if I want to. But the problem with Python is you have to also import the libraries, whereas you don't necessarily have to do that in R if you're careful. So the first thing we're going to do in Python is we're going to import the libraries Panda to create your data frame and manipulate the data, NumPy to perform numerical computations, statsmodels.api to provide statistical functionality, and statsmodels.formula.api. And what that does is that works more like R, and it works with a formula. So that's a difference. They're both stats models, but this is statsmodelsformula.api. Matplotlib to visualize the data, and Seaborn to statistically visualize the data. And so first thing we're going to do is after we have imported our libraries, is we're going to define our variable data, which is we're going to use pandas to read in the CSV file, and then we're going to call it data. And then what we're going to do is there's 3 rows in this CSV file, and one of them is called row names. but I decided to drop that. And the reason why I decided to drop it is because Pandas automatically indexes all of the rows of data anyway. And so since Pandas automatically indexes all the row names, you don't really need to have it. And so I print off the data frame data that's been created, and you can see that we've got one column called weight, and that's the weight of the plant and the group. And so in the group, you've got a control group, you've got a treatment group 1, and then you've got a treatment group 2. And then so what you're going to do is you're going to determine the weights with the group it is. So what we want to do is we want to do a box plot. Since we've got 3 groups, we've got control group, we've got treatment group 1 and treatment group 2. And then, so we're going to develop a box plot for X is your group, Y is your weight, and data is data. And you can see that treatment group 2 has the highest weight, and treatment group 1 has the lowest weight, and the control group is somewhere in the middle. So now, after we created a box plot so we can see how the different weights of the groups fit into the analysis, we're going to do a linear regression. So our Y variable is our weight, and our X variable is the group. And so your model is SMF, that's Stats Models Formulas, .ols, and formula equals Y and a squiggly, I think it's called a tilde, X, and data equals data, and we're going to fit it. And so what we're going to do is we're going to look at the summary. So you can see the summary of this linear regression model. And after we printed off the summary, now what we're going to do is we're going to print off the residuals. And if the residual is greater than 3, it's said to be an outlier. So what we do is we create the influence equals model.getInfluence, and then we're going to obtain standardized residuals. Standardized residuals equals influence.resid studentized internal, and then we're going to display the standardized residuals. And so you can see these are our residuals for our linear regression model. So we can see here, let's see what we've got here. So we've got 30, you've got 30 rows of data, and so that's 1, 2, 3, 4, 5. 5 times 1, 2, 3, 4, 5, 6. 6 columns by 5 rows is 30 rows of data. Now what we're going to do is we're going to make a QQ plot, and the QQ plot will tell you whether the residuals are a good fit. And so we fit the residuals on a 45-degree line, and you can see that the residuals are on that 45-degree line, so it makes a good fit. So now, after we planted our QQ plot and looked at our residuals, we want to perform an ANOVA. So table equals sm.stats.ANOVA LM. So that's an ANOVA on the linear model, and it's on the model, and we're going to print the table. And when you print the table, you get the degree of frequency, degree of freedoms, the sum square, the mean square, your F statistic, and you get your p-value. So we have a p-value of 0.015. So that's like 1.5%. So the p-value is less than the alpha of 0.5. So if you were using an alpha of 0.05, then the p-value would be less than the alpha, and that would be your significance level. And so they would say that there was a significant difference between the the two columns of data or the two arrays. But if you wanted to, you could say, okay, well, our p-value is going to be 0.01. So you have to decide what the p-value is before you actually do the test. And so if your p-value was 0.01, then the p-value would be higher than the significance level, and you would say that the null hypothesis is there is no significant difference between the means of the two columns of data. But so our p-value is 0.015. So if we're using the significance level of 0.05, then we would say the p-value is less than 0.05. So that means that the null hypothesis is there's no significant difference between the two columns of data, and so you would say that you have to reject the null hypothesis, and so you would say that there is a significant difference between the two columns of data because you've got X variable and then you've got your residual. So that's it for the ANOVA for the plant growth. Now what we're going to do is we're going to look at the ANOVA for the R, for the plant growth in R. So first thing we're going to do is we're going to run the program. And as you can see, if you compare the R code to the Python code, you can see that there's a lot less code in R than there is in Python. And the reason why is because all of the formulas that we have used, or all of the functions that we have used, are coded into the R programming language, whereas the functions that we used in Python were not hard-coded into the Python language, which meant you had to insert libraries. So that's the big difference between R and Python. So fortunately, I used the PlantGrowth CSV file that's actually in the R programming language. So that's good because with my compiler, it will not allow me to input CSV files from outside of my compiler. And for that reason, I was able to actually use my compiler in this instance since plant growth is actually an inbuilt CSV file in that. There is another R compiler that will actually allow me to import CSV files, but I'm not crazy about it. I would rather have my compiler because my compiler, I think, works a little bit better, providing you don't have to import any libraries and you don't have to import any CSV files. Because it just won't do that in my compiler. So the first thing we have is our plant growth, data plant growth. You do attach plant growth, and the attach plant growth allows you to use the columns without specifying that it's with data. So you can see we've got the weight in the group, and we've got 30 rows of data. So there you go, 30 rows of data. And then we attach the plant growth, and then we print off plant growth. So you can see that we have printed off the plant growth. So you can see the difference between Python and R is in Python, the first number is 0, but in R, the first number is 1. So that's another difference between Python and R. So now what we want to do is we want to make a box plot of weight and growth. So you can see right here, we've got our box plot between weight and growth. The box plot is very similar to the box plot that we used in Python, whereas you have the control group, treatment group 1, and treatment group 2, and the box plots are essentially identical, whereas the highest weight is with treatment group 2, the lowest weight is treatment group 1, and the middle weight, the control group, is in the middle between treatment group 1 and treatment group 2. So now what we want to do is we want to do a linear model. So we're going to use L mod equals LM weight squiggly group, and I think that squiggly is a tilde, but I'm not sure. And then so we check out our residuals. So you have your minimum, your first quartile, your median, your third quartile, and your max. Those are your residuals. Checks your coefficients, so it just gives you a summary of your linear regression module, and gives you a p-value of 0.1591. And if you remember in Python, our p-value when we did the ANOVA was 0.1591 as well. So we've already printed off our summary, and now we're going to print off the ANOVA, which is the Analysis of Variance table. Again, you got a p-value of 0.01591, which is exactly what we had in Python. So you can see that Python and R, they do exactly the same thing in this instance. They just do it a little bit differently. And the difference is in R, the functions are hard-coded into the programming language, whereas in Python they're not. And I will say that I also tried to do an ANOVA in Excel, because I'm trying to do Python, Excel, and R, and I was not able to do an ANOVA in Excel. So I'm not sure if I'm going to make a video on Excel or not. Excuse me, because it's no point if I'm not able to view the ANOVA in Excel. It's really no point me doing that, but I just thought I would bring that to your attention as well. So I've been talking for quite a while about Python and R, so I'll go ahead and conclude this video. I've talked about what I wanted to talk about, which was ANOVA and its analysis and variance, and I performed an ANOVA on both Python and R. On the plant growth data set. On Python, I imported it as a CSV file, and on R, I used the inbuilt CSV file for that. And I was not successful in doing it on Excel, so I'm not sure if I'm going to make a video on Excel or not. We'll see how I feel. So if you like my video, please like and subscribe. And thank you so much for watching my video, and I look forward to making another video for you in the near future.